All right, good morning, everyone. My name is Alexander Kreis. I am a senior content engineer here at Markforged. And today what we're going to be talking about is 3D printed metal and composite assemblies, or what I like to call hybrid parts. So first, on my slide here, what I have is a metal 3D printed end effector for a robotic arm. Let's talk about this application right here for a second. These are some end effectors from customer Lean Machine. They have this robot arm that they use to transfer these sheet metal parts right here from a tray to a press brake to a receptacle where it gets passed off to the next stage of the process. So one thing that you'll notice right here is there's the reason why these jaws were 3D printed. They were printed on our Metal X that we have here at Markforged. And they have this slightly curved surface at the tip. And the reason for that is to give it clearance so that when it goes into the press split brake, it can clear any of the tooling that might be used to manufacture this sheet metal part. Since the sheet metal parts that this arm is handling is steel, these gripper jaws need to be wear resistant since it's going to be moving hundreds of these parts per day. So when we look at a part like this, can anyone tell me where the gripper jaws will experience the most wear? And you can use this, you can submit where you think it experiences the most wear in the Q&A or in the chat box that I have up now. All right, so again, we're asking where this part, these metal 3D printed end effectors experience the most wear. What we know is, this sheet metal part is being transferred, and most of where it's holding these sheet metal parts is at the tip. So we're getting a few comments, few Q&As in about, the most wear is going to be at the tip, obviously, because that's where it's contacting the steel. Now, in terms of the rest of the part, there's other properties that these printed end effectors need. Strength and stiffness are really important to hold the part securely and minimize deflection when clamping. For example, if the base of this gripper were very flexible, then it wouldn't be able to grip the tip at all. So we need stiffness and strength along the length of the gripper, but we really care about the wear resistance at the tip. Everywhere else on the part, it's not really experiencing that much wear. Another thing that's important is weight. This part weighs about 156 grams. That weight was actually saved because it was printed. The infill geometry inside of this metal 3D printed part makes it lighter than a traditional steel part, which would have weighed at least 2 or 3 times more had it been machined. So that way the arm doesn't need to support as much weight and can move faster. So this is one of the other reasons why it was 3D printed. It could be much more lightweight. And again, because of this slight curvature to the tip geometry, if they were to machine it out of stainless steel, as an example, it would have cost a lot of money and taken a lot of time for them to get this in-house. But instead, they could 3D print it out of metal. And again, that weighed in at 156 grams. But what if I told you we could cut the weight even further by about 50% while maintaining all of these properties? We can do that with what's called a hybrid part. So what is a hybrid part? A hybrid 3D printed part is a part that leverages the strengths of multiple additive manufacturing processes to improve part performance. So we have applied this to this part, where we have, and you can see that right here, where we take that same part and overall geometry, and we isolate just the tip of the part as the metal wear-resistant surface, and we print the rest out of a carbon fiber reinforced composite material. So we save on weight, we save on print time, and we save on cost, and the overall performance is the same, if not enhanced, because the part is just as strong, but about 50% of the weight. What that means for this customer is that the arm can move faster and have higher throughput on its manufacturing line. So this is what we're going to be talking about in today's webinar, this interplay between our composites 3D printers that can print lightweight, very strong parts, and our metal 3D printers that can print very highly wear-resistant parts over a huge range of different geometries. So that's our agenda for today. We already talked about what a hybrid part is. Next, we're going to do an overview of Markforged 3D printing, both with composites and metals, so you can see where some of the advantages lie in each of these technologies. And then we're going to see how that paves the way to produce good hybrid parts. Then I'll show you some different examples of hybrid parts and how they can be put together, different ways you can assemble them, and a few other complementary use cases that involve both technologies. And then we're going to open it up to questions at the end. So first, an overview of the Markforged product lineup and our two unique 3D printing processes. So first, we have our metal 3D printing process. The process here has 3 steps to go from your design to your full metal part. First, you print your part, and this isn't full metal yet. This is a spool of material that's metal powder encased in a plastic binder. Next, you wash that part to remove some of that binder, and then you sinter it in our sinter 1, the furnace we have, to complete the final debind stage. And in the furnace, after the plastic is all debound, the metal powders fuse together across layer lines, and you get your final metal part. So this process is really valuable because it's nearly fully automated. There's no tooling, no setup costs. You just hit print and carry the part through each step of this process. The additive nature of the printer means you have far more geometric freedom, and you can make more complex parts than you might with a more traditional manufacturing method like milling or casting. So you can make complex parts easily, affordably, and quickly. Our composites lineup, on the other hand, allows you to print parts that are as strong as metals with continuous fiber fabrication. So these printers are not like other 3D printers. Typically, plastic 3D printers print parts out of a single plastic material. And we do this a bit differently. We have a secondary nozzle on our print head that can iron down continuous strands of fibers that could be carbon fiber, fiberglass, or Kevlar into a part to make it load stronger than a traditional 3D printed part, again, just about as strong as metal. So it's sort of like putting rebar into concrete. So loads can then distribute around. So this is a cross-section of a part that we have here as a representation. And the loads, if this part experiences any load, those loads distribute around this internal scaffold inside the part to make it really strong. So some other printers print in these like chopped fiber blends, but that can only get you so far because the fibers are chopped up. So the fibers aren't the thing that's distributing the strength. It's still the plastic. But here we have the continuous fibers distributing the strength, and that builds up this really strong scaffold inside the part to make it a whole lot stronger than traditional 3D printed parts. So you can select what reinforcement to use, ranging from fibers like carbon fiber, which you can see here in this GIF. We have, looks like it may be taking a bit to load, but here we have a carbon fiber beam and an aluminum beam, and I think we're having some difficulties with this playing here, but we load each part with about 30 pounds, with a 30-pound weight, and the parts behave the same. So with our composites parts, you can print just as strong as metal, as 6061 aluminum. But you can select from different fibers depending upon what properties you need. So we can print in fibers like Kevlar that produce incredibly tough parts to sustain very heavy impact. So they behave more similarly to materials like UHMW or ultra-high molecular weight polyethylene. Again, I think we're having trouble playing this GIF here, but what we do is we take these little pucks and we smash each one with a hammer. We smash an ABS part, a PLA part, and a Kevlar reinforced composite part. And the PLA part and the ABS part shatter, and the Kevlar part holds up to all of the impacts and blows from the hammer. So with this process, you have the ability to optimize the material characteristics of your part for its loading conditions, putting the fiber where it matters most to get exactly as strong as you need to be. And so when it comes down to when to use what type of fiber, when to use what for your applications, there are some places in which composites may be more valuable. For example, if you need a very lightweight part that's going to be very strong, you'll want to go with composites because it has a high strength to weight ratio. Whereas if you were to go, if you wanted a part that was very hard and very wear resistant, you'd want to go with metal, or very heat resistant. So the composites really perform if you want parts that might need to be very tough, very strong, but very lightweight, very stiff. You can match the strength of a lot of metals and engineering grade plastics with composites. But with metals, you have isotropic strength, you have higher surface hardness, higher wear resistance, higher heat resistance. So depending upon where in your part you need these properties, you can really optimize your design to make use of the benefits of each of these printing processes. And that's why hybrid parts can make such an impact. So some of the other benefits of hybrid parts. So if we look at the print stats of this part that I showed you, where we have this hybrid part next to the original printed metal part, the cost of these are actually flipped. So hybrid part should be here, metal part here. But the cost of the hybrid part is going to be about half the cost of the metal part. The print time is going to be less than half, and the weight again is going to be 50%. So it means that we can iterate a whole lot faster with our hybrid parts instead of printing this entire part out of metal. And each of these parts, the metal parts, they do have to go through the washing and the sintering cycles, which takes the same amount of time, no matter the difference between this part and this one. But what's really important here is it's just really easy to very quickly iterate, print out the strong part where you need strength right here, and the highly wear resistant insert. Someone actually posted a comment about this, and this is exactly what we're addressing. You have a wear resistant insert that you put right here, and that's what's going to be taking most of the wear, whereas the composite part just holds for strength. Some other benefits include modularity, where instead of separate parts with the same base features, you can split up parts to be very modular. So you can swap out, for example, we could swap out different tips depending upon the different sheet metal part that we are working with, depending upon our use case. So that means we could print out maybe 5 different metal modules, but have the composite module stay exactly the same. And that again saves us a whole lot of print time, because we don't need to print out 5 entire metal gripper jaws. We just need to print out the tips. Iteration is another big one. It's easy to allow you to make modifications. This is sort of tied into modularity. So you can reprint part segments as individual components rather than reprinting the entire part. And this further saves cost and time on each iteration. And the other benefit here is that this is all with our metal printers and our composite printers. It's all in one single ecosystem. We have a file management platform, a part and printer management platform called Eiger that allows you to access any Markforged 3D printer. And so you can save parts in folders or in projects and batches so that it's easy to access each of these files and print them off to the printer connected to the Markforged software. To add on to that, because these printers, we've been building 3D printers for about 6 years now, and each printer is sort of we've sort of really figured out how to build a very robust, very reliable, high precision 3D printer. And so across our line, from metals to composites, our printers meet similar quality and tolerance standards that mean that it's easy. You don't have to think too hard about like how the parts are going to fit together, what tolerances you need. It's easy to move from the design methodology from one printer to the other. So you get to think in the same mindset. It's not hard to transfer knowledge from a composites printer to a metal printer when it comes to part design. But the biggest benefit by far is you're able to put the properties where you need them. So you really can optimize your part for exactly where you need certain properties. So now we're going to go into we actually have a question about how uniformity and consistency is maintained while laying down fiber in the material. So basically how it works is, in our software, you can actually sign up for a software trial on Markforged.com and try out our software, which is called Eiger. And what happens is, when you go into the software, you actually go in and you can select exactly where you want to put your fibers. So if you know, for example, in a part like this, actually let's go to the part cam here. In a part like this, we have the composite part here, And what we've actually done in our software is we've said, we know that the strength is all about transferring from these bolt holes to these holes where the metal insert is. And so we can say, I want fiber to route around this path, following basically the outline of this part across all of these layers, or across a specific section of layers. So you actually control where you're putting those continuous strands of fiber down. And that means that, if you know where your part needs to be strong, that's where you can put the fibers. You have control over this on basically a layer by layer basis. So if you know how your part's going to be loaded, then you can put those fibers in. So if we go into detail on this part here, you can see that this part was sort of designed to be, once we printed it, it was designed to sort of be like the final part that they would use. We have these two little holes here that press into the composites part, go through the metal part, and then again press fit into the composites part on the other side with this joint we have here. So this is a very secure way of getting that metal insert embedded into the composite part. It's just this little joint we have right here. And so this would be relatively hard to swap out if we wanted to take this tip off and swap it for a different one. But this tip is generally going to be used for this customer. It's generally going to be used for all of the sheet metal parts that they're handling. So we don't need to worry too much about modularity here. They sort of finalized the part dimensions when they came up with this part. And so this one is, again, about 50% of the weight. So it's a whole lot lighter. That means that their arm can move a whole lot faster. And so that increases their yield on their manufacturing line because they have higher throughput because their arm has a lighter payload. So we're also going to look at a couple other applications. So we have this other set of gripper jaws that we have here. So this one's a little bit different. These pieces carry much heavier machinery. And so we have these composite, again, same story. We have these composite end of arm tooling pieces right here. And what we do with each of these pieces is we bolt in these wear pads into the composite part. We have some threaded inserts in the composite part. They're heat set inserts. They form a very sturdy, reliable connection. And then we just bolt into that. And so we can swap out these wear pads really easily if they wear down after a long time. So since this is a piece of transfer tooling and it's carrying these very large, basically like piping pieces, if these end up wearing down after a long period of time, it's easy to swap them out because each of these prints is a relatively short print job. We don't have to print the entire arm anymore. We just need to print out these little pieces. And that takes much less time and much less cost comparatively to printing the entire arm out of metal. And then we have another example right here where instead we've actually threaded the metal part, the gripping surface, and we've bolted into that with the composite surface from the back. And with stuff like this that's handling sort of heavy equipment, heavy machinery, this type of end of arm tooling, what's really important here is that these braces are very tough. Because if there's an accident on with the equipment and say this runs into a wall, or the handling device that's controlling this, it accidentally drives it too far or something like that. We want this composite part to flex and absorb that energy in case there's a mishap, instead of having it be brittle and snap. You could imagine if this part were a solid piece of metal and you drove the automation equipment too far and this ended up impacting up against a wall or something like that, then if this were metal, it would just snap. Because it's composites, it does have some flex to it, and you can design that flex in depending upon what fiber you choose. So if you choose, for example, a fiber like fiberglass, then it'll have a little bit more energy absorption. So carbon fiber is very stiff, but fiberglass will give the part a little more flex, so that in the case that something goes wrong, the entire part will be saved and you don't need to reproduce it. But even if you did, these prints are relatively quick, less than a day, and these prints again are relatively quick because they're pretty small. So you have that adaptability to change things up and to keep your properties where you need them. So we have a question about what are recommendations or limits for connecting dissimilar material components of a hybrid part. So I'm always in the favor of keeping things modular and making it so that it's easy to take the part off and put it back on again. That can really be shown by this part here. So we have, this is actually 3 pieces that we have. We have this base piece here that mounts to the robotic arm with these bolt holes and these dowel pins to line it up. Then we have this whole piece, which is actually the custom tool. So if we're carrying a certain type of equipment with this, this is held on all with these bolts that go into these threaded inserts that we have here. So when you're working with composite materials and you want to add threads to the part, using heat set inserts is a really surefire way of getting strong threads in your parts. We don't have that example here, but if you put the heat set inserts on the back of your part, then you have a bolt going all the way through to the other side. So if you ever wanted to break this connection, you're trying to pull this tapered heat set insert all the way through the part, which is going to take a lot of work. When you're designing for modularity, you want to isolate those wear segments or the segments that you might want to change out if a different component that you're handling might want to be introduced. So I do recommend these hybrid inserts, these metal inserts for serviceability or replacement, just as was asked in this question, because if these wear down, it's really easy to just pop these out and swap in new ones. The cost of this part, I can't remember off the top of my head. I know these metal inserts probably cost on the order of $10 to $20, whereas these parts, it really depends on what fiber you use and how much fiber you fit in it. These were reinforced with carbon fiber, so I'd expect each of these parts to be on the order of $30 to $50. So totally. So overall, this part would probably cost around $80. But if you ever need to maintenance this, you need to swap out the wear pads or something like that, then all you need to do is print this $10 part to swap that out. All right. So next, we're going to go to this this next application, and this is something neat that that we designed as another demo, and that is this tool handle. So when you're thinking about tool handles, say you have a custom socket head or something like that that you have. Say you have a custom socket head or something like that for a specific piece of hardware that you've had. So there's some examples of this, like if you look at a lot of like public transportation equipment on buses and trains and stuff like that. Often they have tamper-proof bolt heads, and what you can do is they have special tools that are produced in very low volume that they use to assemble all of those. And so this is an example of that, where we might have a custom tool head here that has a specific profile. But since we want this to be ergonomic and we don't want this to weigh 5-10 pounds, we can print this entire wrench handle out of carbon fiber. And this is super stiff. I wouldn't be able to break this. This is just about as strong as aluminum, but it's much lighter. So it's much easier for the operator to use and to maintain. And what you can do is if you have multiple different components, then multiple different tool heads that you need, then all you have to do is swap that tool in. What we've done here is we've designed a little sort of ball detent lock that we have in here. I'll show you that, see if I can hold this up close to the camera. But there's a little spring ball detent in here. It's basically just a little ball bearing with a spring that pushes up against it. And that's what clicks this component in place. So I can go in and I can just push that in, and then I don't need to worry about it falling out. So I can make this very modular and easy to swap out depending upon what tool I'm using. And again, since this is so lightweight, it's not all metal, it's great for the operator and it's very ergonomic. And then we have some other examples. Here's one more case study that I'll show you. This is a sheet metal bending part. Basically, what this customer was doing was they were manufacturing a bunch of these bent sheet metal parts, and they needed a tool to mount to a press brake. And at first they printed this part just out of our carbon fiber reinforcement material. And what they started to see was there was some wear on the tips of these sort of bumps right here that go ahead and actually press the part into the die that we have on the base. And so they redesigned the part. So this block is carbon fiber. And these little pieces here are just these little metal inserts that if you really need to, you can pop out with a pin here. But the metal inserts have a lot higher wear resistance. So along the line, if they do wear down, they can swap out. In general, what they were able to do with a design like this is make parts that they wouldn't have been able to make before. The company that was working on this project, they're a job shop, so they make a bunch of sheet metal parts. And if they hadn't 3D printed their tooling, it would have been too expensive for them to produce this part, because they would have had to machine their tooling, and that would have just been too expensive and taken too long, so they wouldn't have been able to meet the needs of their customer. But because they were able to 3D print their tooling, since they weren't making all too many of these, it was easy for them to print their tooling and to get this job done with these little metal inserts. All right, so I have two more examples to show you. So someone's asking, how much pressure can a tool like this take without breaking? So it really depends on the geometry of the part and where you're putting reinforcement. So in a part like this, you want your reinforcement to be to sort of go along these surfaces, so that when you have a compressive load, the fibers are sort of supporting that compressive load. I don't know exactly what they ran their press brake at, so I can't give you a definite answer. But again, they're bending the sheet metal here, and they're able to sort of do that reliably and repeatably. But yeah, the parts. How I basically describe how the carbon fiber with the fiber reinforcement behaves is you can expect it to behave pretty much like an aluminum 6061 part. And so when you're applying a load to it, applying force to it, that's kind of how you can think about where and when it will deform or it'll break. And that's how you can sort of predict if this part will work. Is our carbon fiber reinforced parts are essentially a drop-in replacement for aluminum parts. We do have another question about skin contact or hearing aids or mouthpieces. As of now, we don't have materials as of now, we don't have like certifications for like implants or anything like that. I definitely know. In terms of if there's going to be a part that has, if there's going to be a part that utilizes like heavy skin contact, we have a different material called nylon white. What happens is the onyx is a little bit, it's a little bit abrasive, so the nylon white is much better for ergonomic tooling if you're going to be holding it or something like that. All right, so I'm going to get to a lot of these questions at the end. I want to show a couple more examples. So one of the really cool things about the printers is, I'm going to bring this part over. I should have left it on the other side. Is that because of that, because they're based on similar technologies, you really can make the parts interact in really interesting ways. So the metal parts, for example, we have, so basically, yeah, what I was trying to say with the question about skin contact and stuff is our materials are not FDA approved. Another question came in about that. So we have, you can use them for some like tooling applications or handling or something like that, but for long-term contact, we don't have that certification. So for interacting with the metal and the composite parts, one of the things that you can do with our metal parts is you can actually machine them after you've printed them, just like you'd be able to do for a traditional metal part. So this is a bearing housing. It's printed out of 17.4 stainless steel. And what we want to do is clean up this internal bore to make room to make a good solid bearing fit. And we also want to clean up this surface grind it so that we have a really great contact surface against the part that it'll be bolting to. And since this is a really odd part, it's going to be hard to make the work holding for it. And so what we can do is we can use our composites 3D printers to 3D print the work holding for this part instead. So I printed that right here. These snap in to the soft jaws that we've printed with composites. I have fiberglass inside of these soft jaws that basically reinforce all of the faces that experience pressure on the part. So that includes these surfaces that we have here, and also includes the top surfaces that may experience pressure as a result of the machine surfacing this face or boring this out where it might be pushing down on the part. So that's where a lot of our composites parts are used, is for these sort of work holding applications. The base material of all of our composites parts, so we have our fiber reinforcement material and our base material. It has a nylon base, and what that means, it's very chemically resistant. So it is resistant to a lot of the chemicals and fluids used in manufacturing. So you don't need to worry about the part dissolving or warping or anything like that. It stays sturdy and it stays solid in the machine shop. Another example we have of that is this tapping fixture. So we had this odd little bracket piece that we needed to print that had a couple holes that we needed to tap in it. So I printed this tapping fixture to support that part, so I could go in with a hand tapper and tap that hole easily. So I don't have to worry about like figuring out how to support this part in the best orientation. The composites parts, again, because the way that the machines are built are similar, so the tolerance stack up is the tolerances are very similar. You can just go in and make a conformal part that your metal piece just snaps into. And all you have to do in that case is just design your metal part, figure out what orientation you want to support it in, and then subtract your metal part with like a Boolean operation in CAD. Subtract your metal part from your work holding body, and clear it out. So I did have to do some touch-ups to this tapping fixture to clear out this segment. But other than that, it's very easy to just create conformal work holdings so that you can do stuff like this, and it makes it really easy to modify your metal printed parts after you print them. And if we go back to the slides over here, then you can see this is actually that needle bearing housing that I was showing you, that being machined out on our mill. So these jaws, they hold up really well in our application. A lot of customers use our printers for this type of application, for soft jaws and tooling in the machine shop. All right, so the general takeaways here are that you can assign properties where you need them with a diverse material portfolio. So if you want toughness but wear resistance, you could print a Kevlar composite body with inserts for metal strength. If you want if you want that stiffness of carbon fiber and you want a little insert for some modularity, then you can print that carbon fiber part on our composites lineup, and you can use the metal part to just print those inserts. So really what you can do, and what I suggest to people when they're designing their part, is once you get to the point where you've brought up your block CAD model, basically, identify where on the part will be experiencing loads and surface contact. Look at the environmental conditions of where the parts can be operating. Sometimes for given parts, I'll draw a free body diagram of the part so that I really know, okay, there's going to be surface contact here, and that's going to be putting pressure on this beam here, which will then in turn put pressure on these bolts that we have here, which then in turn put pressure on and apply a force to the end effector at the bottom. So looking at how the forces travel through your parts, figuring out, okay, the parts that will be experiencing contact with something repeatedly over lots and lots of cycles are the ones that you want to print out of metal. And then the ones that will just be directing that force, you can make out of composite. So all the rest of this section does is direct the force from here all the way down to the end. It's not experiencing any of that wear. So when you get to the block CAD stage of a project, look at, number one, what's your environment? What forces is your part going to be taking and where? And number two, think about that iteration and that modularity. If you think down the line you're going to need to change something up, are you changing the whole thing? Are you changing just a certain feature of it, just a certain aspect, certain mounting pattern or something like that? If you think you will be, then isolate those sections. Are the surfaces that are going to be experiencing wear, those are good elements that you can modularize, right? Because you know that they're going to wear down, and you want to make it as easy as possible for you to replace that part once you get to it. You don't need to manufacture this whole new jaw. All you need to do is reprint out this tiny little bit on the end. So really think critically once you get to the block CAD stage about what you can split off because of like a wear pad or a thing that will experience iterations and might change, and where different sections of your part are experiencing different types of loading conditions. And so then that leads you, what that serves is then you have optimized designs, you have faster iteration because it's easier for you to print the part out or print aspects of the part out over and over again without spending too much cost or waiting too long. You get overall cheaper parts. Again, as we saw with the gripper jaws in the beginning of the presentation, you have parts that are about half the price as if you were to even 3D print them out of metal. And it's all constrained in a single ecosystem. So it's easy to manage all of your files, manufacture them across the system, and get your final part out. So now I'm going to go to our live Q&A. I want to answer a couple of questions that came in before. Somebody asked about the total cost of the 3-part system, the metal system. So the metal system, what you can do is you can talk with a representative on our website and get a quote for the Metal X system. It comes in at about 120K. Our composite system, we do have a lineup from desktop series machines to industrial machines. The industrial machines are bigger, higher precision, and have a lot more qualities that increase their automation. So they're very, very low maintenance. You just send a print to them and let them run, and they'll get you your part out as soon as it's done. A couple other questions. We have some questions about coatings to improve wear resistance or refresh a worn surface. So as I said before, with our metal parts, the point of the metal pads is so that you can really easily just, you know, swap this part out and reprint it so it's good as new when it wears down. We do for our composites, we know that you can electroless nickel plate our parts. For the metal, pretty much anything that you can do to a printed metal part, you can do to that wrought metal. So our parts can be powder coated, passivated, electroplated if you need, you know, that increased wear resistance. But the metals that we're printing in, remember, they are the actual metal that you might be familiar working with. So we have a couple different tool steels that you can print in. We have, including H13 tool steel and A2. We also have 17.4 pH stainless steel. And for each of those materials, you can heat treat them for specific properties. So the tool steels you can heat treat to be a whole lot harder, just like you would with a typical metal part. So if you want that improved wear resistance, you could heat treat it, for example. If you want to refresh the worn surface, you know, reprinting it will get you good as new quality. But again, if you need to machine it, if you need to polish it or coat it, you can do that. You have that option. There's some other questions. We do have a question about permeability. So the onyx, the composite parts are they're not watertight because of the printing process. They get built up layer by layer, so they're semi-porous. Again, there are coatings that can fix that, so you can epoxy coat it if you need it to be watertight or something like that. All right, any other questions coming in? All right. So we got a question about heat transfer. Which of the materials is best for a heat sink? So I would definitely look on our website. We have a lot of materials listed there that are released or that are in beta. In terms of heat transfer, I don't know if we have something right now, but we're always updating our roadmap and coming out with new materials. So I would definitely talk with a sales representative about what would be a good option for that. In terms of our composite parts, so again, the metal parts act just like their like wrought metal material. The composite parts have a heat deflection temperature of about 150 degrees Celsius, and we have a specialty high temperature fiberglass that you can use if you need strength at high temperatures. So you can actually use parts like our composites parts for welding fixtures, for example. Stainless steel is often used as a heat isolator. So if you're in contact with a hot surface, if your metal wear pads are in contact with a hot surface, that'll isolate the heat pretty well so that it won't really have an impact on the actual composite part. We have another question about soft printable materials for gripper pads. So as I mentioned earlier in the presentation, we do have a nylon material that you can print out of. That's probably the softest that you'd get. Depending upon how you design it, you can make it a little bit more flexible and have a little bit more give. And so you can sort of design flexural elements with that, where you can make things that are a little more compliant and bendy. And if you're looking for like parts that absorb a lot of energy, that can bend a lot, our Kevlar is probably our toughest. It is our toughest fiber. So the Kevlar reinforcement on like a nylon part is probably where you could get like a long-term durable solution for a softer but still durable material. All right. So we're just getting a couple more questions in. We have a question about simulation tools for performance prediction. One of the things about the composites and 3D printed parts in general is that they are pretty hard to simulate, right? As I said, the composites reinforced parts behave pretty similarly to aluminum, but it really does depend on the geometry. And because you choose where you're putting the fibers in, where you're reinforcing the part, you can say, you know, oh, I want 2 rings of fiber here, or 8 rings, or 10 rings, and that will increase your part performance, increase your part strength. But in general, it is kind of hard to predict how the composite parts will behave. All right. And we got a question about autoclaving composite materials. I'm not too sure about that. You may need to talk with one of our product experts about that, figuring out what the process would look like. Certainly, if it has a if it's going to be at 121 degrees Celsius, as it says in the comments, that should be a good application if you're using composites for our high strength, high temperature fiberglass, because we can really maintain heat at those higher temperatures in the 100 to 200 degrees Celsius range. All right. If we don't have any more questions, thank you all for joining the webinar. If you need any more information, you can learn more at markforged.com, where we have recordings of previous webinars. We have design guides and tips and tricks. We have other white papers, and you can also get in touch with a product expert who will be able to walk you through what kind of machine you might be looking for, so that you can make an educated decision about what kind of printer would be best suited for your application. Thank you so much, and have a great day.